So here's a graph, and then we want to come up with the equation. Okay, and so we know they're polar conic sections. We want to come up with that, and then obviously want to write the equation of the directrix. Okay, so I'm actually going to start with example C, which is the parabola. So we know that the eccentricity of a parabola is exactly 1. That actually really makes the equation a little bit more simple, knowing that fact. So, and the other thing I want to remind ourselves of is that we know the directrix is like somewhere over here, right? And so because the directrix is somewhere over there, we know it's a negative cosine function. So I know I'm going to start off by saying r equals, and I know it's going to be 1 minus cosine of theta. And again, two things, we always want to have our standard form as having 1 in that first coefficient, and we know our eccentricity is 1, right? So we know that we know that this coefficient in front of there has to be equal to 1. So then the other thing we can think about is sort of like, how do we find this E times P that sits up there? And it goes back to knowing what happens in the off axes. Like cosine does things on the x-axis, but cosine does nothing on the y-axis. And if you take a look on the y-axis, we've got these values of 5. So if I'm putting in 90 degrees and getting an output of 5, since the cosine of 90 gives us nothing, we know that this has to be a 5 up there. So, again, just looking at that off axis is going to help us. And if it were a sine function, then we know the off axis of sine wouldn't have been the x-axis. So now that we have the equation, we do know that this 5 represents E times P. Let's go to orange here. So 5 equals E times P. Since we know our eccentricity is 1, we know our p-value is equal to 5. And so that's 5 units from the pole. But remember, it's always behind. So if we go 5 units, we're sitting like right here. And here's our directrix. Right there, a vertical line. Now, a vertical line would have been x equals, but since we went the polar version, it's r equals negative 5 secant of theta. And again, just to confirm, that ratio has to be a 1-to-1 ratio. That's how we defined our, our eccentricity. And it is like this distance here is 2.5. This distance here is 2.5. That's a 1-to-1 ratio. This distance here is 5. This distance here is 5. 1-to-1 ratio. Any point that you pick on the parabola, again, you measure it to the directrix, you measure it to the pole, it'll be a 1-to-1 ratio. So I always think that parabolas are the easiest to get the equation because you know that this coefficient must be a 1, and then you can just go to the off axis to find the numerator. Okay, so let's go to our next one. Let's go to an ellipse. Okay, so for our ellipse, remember this is our only focal point. It's a little bit different, like we had said in the first video. And the directrix is always found on the shorter end, right, of the ellipse. So our directrix is going to be somewhere up here. And the fact that it's somewhere up there tells me it's a positive sine function. And again, that's sort of like recognizing these shapes. And it's a bit deceiving because even though the bulk of the sine graph, of the ellipses seems, it is on the negative y-axis, our function is going to be positive sine because it's based on the location of the directrix. And the directrix is always on the shorter end of the ellipse. So I already know it's going to be r equals, and it's going to be 1, and it's going to be plus some number sine of theta. And, again, I would go to the off axis because sine does nothing on the x-axis. So when I'm looking here at 6 and here at 6, the only time that is possible is if there were a 6 up here, right? Because sine does nothing at 0. So if you kind of like temporarily ignore this, like that's a 0. The only way you're going to get a radius of 6 is if you have 6 divided by 1, which is 6. Okay, so at least we have that coefficient. So then what I want to do is kind of look at, I've got up here at 90 degrees, I have a value of 4. And at 270 degrees, I have a value of 12. So, you could think about like trying to solve this, like, oh, when I put in 90 degrees, I know my radius is equal to 4. So when I put 90 in for sine, I know 4 is equal to 6 over 1 plus sine of 90 is 1. But remember, we don't really know what this coefficient is. So we can call it e if you want. E times the sine of 90, which we know is 1. So I have this equation 4 equals 1. 6 divided by 1 plus e. You could multiply that 1 plus e over, so 4 plus 4e is equal to 6. Subtract the 4. 4e is equal to 2. So e is equal to 1/2. So now I know this coefficient should be a 1/2. And you can even try like plugging in 270 to see if that works. So we can do a quick check. I guess we'll pick a different color, maybe this darker red. So quick check. Do we in fact get, like if I say r equals 6 over 1 plus 1/2 sine of 270, which we know is -1. Oh, sorry. So that's r equals 6 over 1 minus 1/2. So r equals 6 over 1/2, which is 12. Fantastic, we did it. Okay, so just kind of a check. But ellipse, again, you go to the off axes just like we did with parabola. And we could either do by inspection or solve by an equation. Okay, so now that we know that this is equal to 1/2, we can solve for our directrix, because remember, 6 is equal to e times p, right? The number that sits up there. Since we know our eccentricity is 1/2, that means our p-value would have been equal to 12, and that's 12 units above our focal point. So we know that our equation would be r is equal to 12 cosecant of theta. And again, we could do a check. So if you take any point on the ellipse, let's say we take this point right here, which is 6. You measure 6 to the pole, that's a distance of 6. You measure this point up to where the directrix was, which was 12 units away, that's 12. 6 to 12 is a 1:2 ratio, right? Pick this point right here, which is 4. This is 4 units away from the pole. If this is at 4, then it's 8 units away from the directrix, which is at 12. And again, 4 to 8 has the 1:2 ratio. So again, just trying to connect this eccentricity. It's constant no matter where you're at on your ellipse. Okay, last, the hyperbola. So the hyperbola, it makes it just a bit more tricky because both points are on the same side of the axes. So that means one of those distances has to be negative. So it does get a bit tricky. But we can solve this, and it's not we're smart, we can figure it out. First thing we got to remember is what kind of function is this? And again, since a directrix lies somewhere in between our branches, we know this is going to be a negative cosine. And remember, it's not going to be centered. It's not symmetric. So we know it's going to be a negative cosine. So r equals 1 minus something, and there's a cosine, and we have to solve for that coefficient. So we're not really sure what that is. But we can still figure out the numerator by looking at the off-axes, right? The off-axis of cosine, once again, is the y-axis. So notice there's a 6. There's a 6. So we know that this has to be 6. And again, how do we know this? Because when cosine of 90 or 270 is evaluated, this whole expression becomes the 0, right? So the only way we're getting 6 is if there's a numerator of 6. Fantastic. So now we have to find this. So when we put in 0 degrees, right, when we put in 0 degrees to this, because this coefficient is more than 1, right, when you think about this, when I put in 0 degrees, because this coefficient is more than 1, 1 minus something that's bigger than 1 is going to give us a negative value. So it sort of makes sense that like this point really like this point or this point has to have a negative radius. And so that becomes a little bit tricky. So if I think about, okay, so that could be a 2 or it could be a 6. So what so that's where we have to kind of figure out like there's a little bit of, I was guess and check, but just to kind of check your work, and kind of and check, just to see which one would it work out to be. So when I put in 0 degrees, um, the radius is either going to be -2 or it's going to be -6. So that's why I have to kind of check, like which one makes sense. And because then whichever one it is, like if I pick negative, if it's 0 degrees, it's -2, that means at 180, it's 6. Or if it's -6 when it's 0 degrees, then it's 2 when it's 180. So only one of these pairs works. So it's either this pair or it's this pair. So that's what makes the hyperbola a bit more tricky. So let's see what happens. If I put in 0 degrees, let's see what, like if I put 0 and 180, let's see if I can get that. So we know the cosine of 0 is 1, and what happens if I get a -2? So let's think it's -2 equals 6 divided by 1 minus our mystery number, right? Because we know the cosine of 0 is 1, so all we're left with is that mystery number. So if I multiply this over, this quantity over, that becomes -2 plus 2e is equal to 6. And I add my 2 over, so 2e is equal to 8. So e is equal to 4. So if I put a 4 in for that question mark, let's see, r equals 6 over 1 minus 4 cosine of theta. Well, it does start off great because our eccentricity is already greater than 1, which we know that's hyperbola. Let's see what happens if I put 270 in there. If I put 180. If I put 180 into that, let's see what my r is. R equals 6 over 1 minus, well, the cosine of 180 is -1. So that becomes 4 times a -1, so it's -4, so 1 plus 4. So then I end up getting r is equal to 6 over 5, 6/5. Well, we were expecting at 180, we were expecting 6. So it doesn't seem like that's right. So let's then switch it out and say, okay, so that we chose wrong. So it must be then the other one. So let's just double check to make sure that's okay. Erase this, erase this, and we plug in the second one. So let's try, there it is. So let's try when we get an r equals 0 to get -6 as my radius. Oh, sorry, when theta is 0. So -6 equals 6 over 1 minus our e value. And again, we're saying cosine of 0 is 1. So then we get 1 minus e. So we move this over. So we get -6 is equal to 6e. Oh, sorry. Let's try doing algebra. My bad. -6 plus 6e is equal to 6. We add the 6 over. So 6e is equal to 12. So e is equal to 2. Again, eccentricity greater than 1, so that fits. We just have to make sure it works in the other point. So r equals 6 over 1 minus 2 cosine theta. Let's see if that works. If we put in 180, what do we get? 6 over 1 minus 2 times -1. So r equals 6 over 1 plus 2, which is 3. So r is equal to 2. Fantastic. That, we said we only were going to get one of them, and it works out perfectly. So that's why I saved the hyperbola for last, because both points lie on the same side. So one of them has to be a positive radius. One of them has to be a negative radius. Now, as you start solving, maybe you're going to find a pattern. Maybe the one that's farthest to the left is always going to be your 0. And even if I already knew that to be true, maybe that's something you could find out too. Okay, so now we get the equation, right? We know the equation. We just need to get the directrix. 6 is my E times P value. If our, if our, let's see. Oh yeah, so if our, sorry, crazy brain fart. If my eccentricity is 2, so that means our P value is equal to 3, and it's 3 units away from the pole, so it's on the negative side. So r is equal to -3 secant of theta for that vertical line. Okay, fantastic. And again, we should see this eccentricity of 2. So if I say 1, 2, 3, so if this truly is my directrix, let's check. So this point is 2 units from the pole, 1 unit from the vertex or from the directrix. That's a 2-to-1 ratio. This right here is 6 units from the pole and 3 units from the directrix, 2-to-1 ratio. Like this point right here is 6 units from the pole, 3 units from the directrix, 2-to-1 ratio. So, again, I think if you look at the 3 different conic sections, certainly the ellipse or the hyperbola is the toughest one, but not impossible.